Hi there, my name is Avon George. I recently graduated from Boston University with a bachelor's degree in computer engineering, and I'm speaking on behalf of my mentors in this project, Anthony Byrne and Professor Isaac Joskun, to talk about our research, MicroFaaS on OpenFaaS, an embedded platform for cloud functions. I'd like to first give an overview of the motivation for this project that starts with the story of cloud computing. Cloud computing was predominantly driven by the need for efficiency. For example, we started moving servers into co-location centers where land is cheaper. We started multiplexing servers with virtualization, meaning multiple virtual machines can run on a single hardware platform. And all these improvements were focused on efficiency, more precisely, cost efficiency, resource efficiency, and scalability efficiency. However, with this increase in demand for cloud computing, the power consumed by data centers also increased. The statistics from 2020 shows that 1% of global power consumption was consumed by data centers. And typically these data centers use x86 rack servers. Our solution, MicroFaaS, which is a function-as-a-service focused data center hardware model, suggests the use of smaller scale, energy-efficient hardware. In other words, the use of single-board computers as an alternative for running serverless functions. This way we can ensure that these serverless platforms are now more energy efficient. So what is FaaS? So FaaS is a cloud-based software used to deploy and execute short-lived, stateless, and loosely coupled functions, also known as lambdas. And the benefits include greater scalability, reduced development time, and easier maintenance. So the current implementation of FaaS uses x86 servers, and it runs on either virtual machines or containers that are running on these x86 servers. And some of the disadvantages of this platform or this model is performance variation, and due to the nature of the workload functions, we also get unpredictable cold start latency. Instead, the proposed solution, MicroFaaS, aims to run each serverless function on an energy-efficient, hardware-isolated, virtualization-free ARM-based node. So for the MicroFaaS architectural overview, we chose inexpensive, low-powered single-board computers that represent a node or a CPU that runs each serverless function. And each of these nodes use a bare-bones Linux kernel that was heavily optimized in order to lower the boot times. We also use an execution model that's different from current cloud implementations. One, we use single tenancy, which means that when each node is running a function, nobody else will be able to use that node at the same time, meaning only one function runs in a node at a certain time. And we also use run-to-completion model, which essentially is each node or CPU runs and completes a certain function before moving on to the next. And then we also have our security model, which is closely related to the execution model. So we have hardware isolation, which means that your function will not run on the same physical machine as anyone else's code. So this way, any risk of a program that modifies another program is nullified. And similarly, we also use a post-execution reboot, which ensures that the previous function does not influence the new function being executed. So the post-execution reboot is essentially after each function is executed on a node or CPU, the node and CPU reboots before executing the next one. And finally, we have our energy model, which essentially makes sure that each CPU or node powers down after it runs the serverless function and when there's no other functions left to run. So in our prototype, we use 10 single-board computers that work as the worker nodes, all of which are connected to the same network using a switch. And then we use one BeagleBone Black as the orchestrator node that receives the function request and turns on the appropriate worker nodes and sends the function request along with the inputs of the function. And each of these worker node is prepared with MicroPython, and it's heavily optimized using an iterative process as seen in the figure to get the boot time to about 1.5 seconds, which is two times lower than what the original boot time was. In order for the users to run and execute the functions on MicroFaaS, we implemented an OpenFaaS plugin. So what is OpenFaaS? It's an open source framework that allows users to execute serverless functions without worrying about the infrastructure. And why we use OpenFaaS? Essentially, it gives users a simple and easy to use interface to run these serverless functions on MicroFaaS. And how is this implemented? So MicroFaaS uses the OpenFaaS gateway to link the web user interface with the provider's HTTP endpoint. So the provider in our prototype is what we call the orchestrator that is responsible for getting the function request from the OpenFaaS web UI and sending the functions along with the inputs to those functions to the worker nodes. And subsequently, once the worker completes or executes the serverless function, it gets the output to the function and sends it back to the OpenFaaS web UI. In order to evaluate the energy and the execution performance of MicroFaaS, we ran 15 commonly used fast functions on both MicroFaaS and x86 server, which in our case was a 12-core AMD processor. And to have a fair comparison between both the models, we compared running each function between 1 to 10 workers for MicroFaaS and 1, 6, and 12 threads on the x86 server. And the table here shows all the fast functions that we ran, along with a brief description of what these functions do. And all these functions were adapted or inspired from a function bench GitHub repo. Before executing the experiment, we did a function profiling on all the workload functions to determine whether the functions were either network intensive or CPU intensive. And to do so, we used perf and nload, which are utility functions. And the table or the figure below shows the results. And we can see how PSQL purchase and PSQL inventory uses a lot more time with networking, so it's considered a more networking intensive function. And functions such as PIEs, which is an encryption function, uses more computation or spends more time on the computation. So for our experiment, we ran each function for 1,000 iterations on both MicroFaaS and x86 server. There's your terminology here: execution time and overhead time. Execution time is simply the time taken to run each function, and the overhead time is the additional time on top of the execution time, which is the result from calling the function from OpenFaaS and sending the function along with the inputs to MicroFaaS and getting the output back from MicroFaaS to OpenFaaS. So it's just the additional time. And the below two figures show the results that we obtained. And it must be noted we have two figures because they have different time scales. The one to the left is from 0 to 10 milliseconds, and the one to the right is from 0 to 300 milliseconds. And from these figures, it's clear that the server, the x86 server, spends less time executing each function. And this is quite what we expected, because the x86 server has a better network card and a faster processor. Then for the same experiment, we observed the energy performance. So here's the throughput graph, and clearly we can see that MicroFaaS has an inferior throughput when compared to the x86 server. However, when we compare the energy use, which is the energy to run each function, or joules per function, we see that MicroFaaS does a lot better than the conventional server. In fact, MicroFaaS on average consumes 20 joules to execute a function, while the x86 server consumes approximately 40 joules. And then here we see the average power consumption for both models. And we see that at most MicroFaaS uses only 25% of the power consumed per function compared to the x86 server. And another important thing is that MicroFaaS has a linear power consumption, which means that as we increase the number of workers, the power consumed increases linearly. And this shows that MicroFaaS has an energy proportional design to it. So when no workers are running, it uses 0 watts. However, that's not the same case with the x86 server. When it's not running, when it's at its idle state, it still uses approximately 60 watts. Then we ran a MicroFaaS cost analysis. So we compared the cost of running both the conventional serverless platform and MicroFaaS over a 5-year period. In the conventional case, we used 41 servers and 1 top-of-rack switch. And in the MicroFaaS case, we used 989 single board computers, which provide the same throughput as 41 x86 servers, along with 21 top-of-rack switches. And in the ideal scenario, we have 100% utilization and 100% online rate, which means that over these 5-year period, the nodes and the CPUs are being constantly used. And the online rate, 100% online rate, means that nothing breaks over these 5-year period. And here we see that MicroFaaS requires a lot less money when compared to the conventional serverless platform. And then realistically, we have 50% utilization rate, which means that only 50% of the time are these serverless platform and MicroFaaS being used, and a 95% online rate, which means 5% of the nodes will break over the 5-year period. And even in this case, we still see that MicroFaaS requires a lot less money than the conventional case. And in fact, MicroFaaS is 33% cheaper than the conventional platforms. To conclude, we see that MicroFaaS is 2 times more power efficient than conventional rack servers. Moreover, MicroFaaS is 33% cheaper than x86 based rack servers. And this is essentially due to the inexpensive single board computers and the energy proportionality design of these single board computers on MicroFaaS. So in a sense, MicroFaaS and OpenFaaS provides an energy efficient and cost efficient alternative to standard fast platforms. Thank you for listening. If you want to know more about our research or more about MicroFaaS, I encourage you to visit bu.edu/pclab. And this project is open source, so if you want instructions and scripts to make your own MicroFaaS, I encourage you to visit github.com/pclab/MicroFaaS. Thank you.